Hi guys, it's been a while since I have uploaded any videos to YouTube. So I have this one topic that was not discussed about the three heat transfer modes. It's called the radiation heat transfer, and in today's video we are going to look at it. So I also made the same videos in Bangla language, and if you are interested you can find that in my YouTube channel. So without further ado, let's dive into radiation heat transfer. So previously we have looked at the other heat transfer modes. The first one we looked at was heat conduction, and basically it's the mechanism of how heat can pass through different types of material, say for example solid materials or fluids. By fluids we refer to both liquids and gases, and in all those cases we looked at heat can be passed through the materials because of the translation, rotation and vibrational motions of the particles that made up that material, so the molecules. When we talk about how heat can pass through a solid or fluid, so between a solid or fluid surface to a moving fluid, we are actually talking about heat convection. So this is the mechanism through which heat can be transferred from any kind of surface, be it from solid or liquid or gas, to a moving fluid. So solid to liquid, it can be done with heat convection. Solid surface to a gas, it can be done with heat convection. From a liquid surface to a gaseous surface through heat convection, yes, it can also be done. So today we are going to look at the third mode of heat transfer, which is called the radiation heat transfer, and this is very important because through this process heat can pass from one material to another material without the help of any medium in between them. If there is a medium, it's fine, but it's not necessary. So in this video I am not going to go into the detail of the physics of the radiation heat transfer process. So we will just take away the lessons from physics and try to apply to our engineering applications. And the first thing we know from physics is energy is emitted by matter at almost any temperature. So if a material is at a finite temperature, be it 25 Kelvin or 500 Kelvin, it always emits energy in the form of radiation. And when we talk about radiation heat transfer, we actually refer to this energy, and we can actually feel that energy. So imagine you are standing in the middle of a field exactly at noon, and there is a bright sun that is shining its rays on you, and you will start to feel warm, which means that the energy from the sun, which is a million miles away almost, and it's being transferred to your body, and so you can actually feel warm. So the process through which it was transferred from the sun to your surface of the body, that is via radiation heat transfer. So we can ask ourselves why this process takes place, and the reason is because matter is constituted of atoms and it has electrons in it, and the electrons are configured in different ways in different matter, in different molecules or in different substances. And if there is any change in this electronic configuration of a substance, we get radiation heat transfer. So for example, if the electrons have higher energy, they can release some of their energy and go back from a higher energy level to a lower energy level, and when they go back to that lower energy level, they release their balance energy. So that extra energy they had when they were at a higher level, they can release it, and that release is in the form of radiation. An important concept is energy is transported by electromagnetic waves or photons, and for these photons to travel, they do not really need any medium. If there is any medium in between them, it might slow them down, but it's not really necessary for these electromagnetic waves to travel in a space, and because of that, radiation heat transfer does not require any medium. And this process is most efficient in vacuum. So if you have nothingness, so there is nothing, no air, no other gas, liquid or solid or anything, this radiation heat transfer process is going to be the most efficient. But if there is any other material medium that is present when this wave is going on through its path, it can still take place, but it will not just be as efficient if it was taking place in a vacuum. So this is quite different from conduction and convection heat transfer, because both of those two, they need a material medium to take place. But as we just said, radiation heat transfer does not need any medium. So that is a particular advantage or disadvantage if you think about engineering applications, because you may not want unwanted heat transfer from your product or your process, but because of radiation, there is always going to be some heat transfer. But we often make simplifying assumptions to either neglect that or to counter that. So another important thing to keep in mind, radiation can occur from any surface, be it from solids, liquid or gas. It can occur from any surface. But in this lecture, I'm just going to keep things simple by talking about only radiation heat transfer from solids. So whenever I mention radiation heat transfer is taking place, I'm actually referring to radiation heat transfer from the surface of a solid. So we have to know about one concept that's called emissive power. And in order to understand that, let's consider a surface, and let's assume that the surface temperature is represented by T subscript S, and around this surface there is a gas. Temperature of that gas is T subscript infinity, and it has a heat convection coefficient of H. So because there is a gas around the surface, and that gas might move or it can be static, it does not really matter, but that surface can interact with that gas and transfer heat via heat convection, because we have seen before that heat can be transferred from a surface, from a solid surface or liquid surface or gaseous surface, it doesn't really matter, to another moving fluid via heat convection. So the idea is the surface, it has some thermal energy because the matter is made of molecules and they have motions, translations, rotations, or vibrations, and because of that it is sort of has a default thermal energy that is always there, and it can exchange some of that thermal energy to the nearby gas via heat convection, or if there is any other material it can also exchange that heat via heat conduction. So because of the motions of the molecule that is inside the matter, the surface has some thermal energy, which we often call bounded thermal energy because it's in that surface, and some of this bounded energy can be released or emitted by the surface when radiation heat transfer is taking place. So because of the change in electronic configuration and because the surface is at a finite temperature, some of that energy can be released, and that is what we are showing via this E symbol. So now we are going to define something, and we are going to call it emissive power, E subscript B, and the emissive power is the rate at which energy is released per unit area from that surface. Since it's the energy released per unit area, and we know the unit of energy generally joules, but when we are considering energy release or heat transfer, we refer it via watt, so energy transfer per unit time. So that is the watt, and because the energy is being released per unit area, we are calling the unit of this surface emissive power watt per meter squared. So now there is a question, can a surface release energy forever from its bounded thermal energy? So whatever energy it had previously, can it just continuously emit it? Turns out no, it can not release energy forever, or it cannot release energy on any amount it wants. So there must be some upper limit to the energy that a surface releases, and we can figure out the upper limit to this emissive power using a law which is called Stefan-Boltzmann's law. And this law primarily says that whatever the surface emissive power E subscript B was, it must be proportional to the surface temperature. So we have already said the surface temperature was represented by T subscript S, and the surface emissive power is represented by E subscript B. So the Stefan-Boltzmann's law, these two quantities are not only proportional, but it is proportional in such a way that the surface emissive power is proportional to the fourth power of the surface temperature. So we can remove this proportionality sign with a constant sigma, and if we do that, we get the equation in the red box, and this equation EB equals sigma times T subscript to the power fourth. So that's the mathematical statement of Stefan-Boltzmann's law. From this, we can also learn about some important things. First of all, in order for this equation to work, we must use T subscript S in the units of kelvins. So basically this T subscript of S, it represents the absolute temperature of surface. It's fine if you measure it in Celsius or Fahrenheit, but if you want to use it in Stefan-Boltzmann's law, it has to be in kelvins. So the second thing is, we can do a bunch of experiments and we'll find out that the emissive power and the surface temperature in absolute scale or Kelvin scale, they are related in this way, and the proportionality constant has a value or magnitude of 5.67 times 10 to the power minus 8 watts per meter squared Kelvin to the power 4. We have already seen that the surface emissive power has a unit of watts per meter squared, and we're just dividing it by T subscript to the power 4 because we just changed the sides of the equation in the red box. Thus, we can find out the value of the Stefan-Boltzmann's constant sigma. So now there is a catch. The question is, does all surfaces obey Stefan-Boltzmann's law? So if a surface obeys Stefan-Boltzmann's law, that is, for a surface, if we can measure its emissive power and we can measure its surface temperature, and then use this equation EB equals sigma times Ts to the power 4, and that is valid for that surface, then we can call the surface an ideal radiator or black body. And there is an example of this. So let's create a cavity with a small hole, so all the incident radiation can enter that cavity and get absorbed by it, and if you then get that cavity to release all that energy, if it releases all of that energy from its surface and it obeys the Stefan-Boltzmann's law, we would call it an ideal radiator or black body. So the important thing to keep in mind, if a surface is called an ideal black body, that means it will obey Stefan-Boltzmann's law, and we can calculate the surface emissive power of that black body actually quite easily, because we just have to use this formula, EB equals sigma times Ts to the power 4. However, if a surface is not an ideal black body, then it will not obey Stefan-Boltzmann's law, and we may have to make some modification to it. What can we do for real surfaces which are not ideal black body? So for a real surface, so this time we again have a surface, and we have the surface temperature Ts, and there is a gas around it, and the surface can exchange heat to that gas via heat convection, and it can also release some energy E. But this time we have introduced a new quantity called emissivity, epsilon, and we're being careful, so we are measuring Ts in terms of kelvins. And instead of calling this surface ideal black body, let's consider it to be a real surface, that it may not be a black body. So for a real surface, turns out the thing is very simple. It always emits less energy compared to a black body at that same temperature. So for real surfaces, we have to modify that equation and come up with the equation in this blue box, where we are saying that compared to a black body, a real surface, whatever energy it releases, it's represented by E, it's going to be less than whatever a black body releases. So a black body has a surface emissive power of E subscript B. The subscript B refers to it being a black body, and we are saying, okay, a real surface will always have less energy emitted per unit area compared to a black body. So how can we calculate that energy per unit area that is being released by a real surface? And the way to calculate it is basically we are going to just modify the Stefan-Boltzmann's equation a little bit. So we take out whatever that EB value was. So the EB value was given by sigma times Ts to the power 4, and we're just multiplying it by a factor epsilon, and we can use this equation to then calculate E. So depending on the value of epsilon, E can be equal to sigma times Ts to the power 4. So that means if epsilon is equal to 1, it is going to give us the same equation of Stefan-Boltzmann's law, and then we can actually write E is actually equal to be EB, or that means epsilon equals 1 refers to a black body, but any other value of epsilon rather than 1 would mean it's not a black body. So does that mean we can use epsilon greater than 1? No, not actually. That would mean that the real surface is emitting more energy compared to a black body, which is not possible. So now it's a good time to define emissivity. Emissivity is a radiative property, and it's a measure of how efficiently a real surface emits energy compared to a black body. And we also learned that if epsilon is equal to 1, that means the surface we are talking about is actually a black body, because it's giving us that same equation of Stefan-Boltzmann's law. But epsilon can be 0. If it is 0, that means the surface is not emitting any energy. So epsilon has a bound. It can only take values between 0 and 1. We can just summarize what we learned about emissivity. It's a radiative property. It measures how efficiently a surface can emit energy compared to a black body. It values falls between 0 and 1. But importantly, its value depends on the surface finish. So if the surface is polished, it might change its emissivity value before it was polished. And it can also depend on the surface material, because depending on which kind of material we use to make a surface, they have different molecules in them. So there is different kinds of electronic configurations possible, and because of that, the amount of energy that can be released, it can also change. So I can give you an example. Aluminum has emissivities. When it is polished, its emissivity is 0.03, but when it is anodized, its emissivity is 0.84. And importantly, the emissivity value, it must be stated at a particular temperature, because it can also vary with respect to temperature. So these two values are only valid at temperature of 300 Kelvin. So we are going to now talk about the exactly opposite thing. So till now we have talked about energy going out from a surface or being released from a surface. So now we are going to talk about what happens when energy is incident on a surface, so a surface can absorb it. Some examples would be, we can have sun rays falling into our house and warming it up. We can put some food in an oven, and the hot walls of the oven can emit energy and heat our food up. So again, we take a surface and we're measuring its temperature with T sub S, which is in kelvins. There is a gas, and the surface can exchange heat via heat convection. It can release some energy E, and we know how to calculate that. This time we're also saying there is some energy that is being incident on this surface. So we are representing that by the symbol G. So depending on whether this energy is coming from the sun or from hot oven walls or from any other source, it can have some effect on the radiation heat transfer process that takes place. But we are going to define this G and we are going to call it irradiation, and we are going to define it in such a way that it does not capture the effect of the source of the radiation. So irrespective of source, we are going to call the rate at which all radiation that is incident on a unit area of the surface the irradiation G. So it primarily means that whatever energy that is incident on a surface or falls on a surface, and if it's absorbed by the surface, then we're just going to calculate whatever energy that was absorbed on a unit area, much like emissive power, and we're going to call that amount of absorbed energy irradiation, and we're going to represent it by the symbol G. So there is a new quantity also, much like emissivity epsilon, we have a new quantity called absorptivity alpha. And the reason it is there, much like a real surface was unable to emit as much energy as an ideal black body or a ideal radiator, a real surface may not absorb all of the incident radiation, and we need to take that into account. So what we are saying is portion or all of the radiation may be absorbed by the surface and increase its thermal energy. So the surface has bounded thermal energy in it, and whatever energy it's absorbing, it might increase its energy content. So now we are going to try to quantify how much energy that is actually absorbed by the surface. So whatever incident energy that was falling on the surface, we are calling it G, and depending on this surface's ability to absorb energy, it might absorb all the energy that was falling on it, or it might absorb a portion. So we're going to multiply that Z value with alpha. So imagine if there was 200 watts of heat that was falling on you, and the absorptivity of the surface of your body alpha is 0.7. That means actually you are absorbing, or your surface is absorbing 200 times 0.7 or 140 watts of energy. In order to quantify the amount of absorbed energy, we actually use this parameter called alpha, which is absorptivity. And much like emissivity, absorptivity is also a relative property which provides a measure of how efficiently a surface absorbs the irradiation. So irradiation was whatever the amount of energy falling on unit area of a surface, and now we have defined the absorbed irradiation G ABS, G subscript abs, as alpha times G, which refers to the fact that actually absorbed amount of energy is less than the irradiation. So much like we just saw the discussion of an ideal black body and a real surface. So if alpha is equal to 1, that means all the energy that was incident on the surface was being absorbed, and if alpha is 0, that means no energy was being absorbed, so there was no absorbed irradiation. So absorptivity actually means the rate at which radiant energy is absorbed per unit surface area. And much like emissivity, both absorptivity and emissivity are radiative properties, and their values falls between 0 and 1, which you already understood. For an opaque surface, if alpha is less than or equal to 1, it means that some of the incident radiation G must be reflected. And if the surface was semi-transparent and alpha is still less than or equal to 1, that means some of the incident radiation could be transmitted and some of it could be reflected. The way to understand it would be, so imagine there was 200 watts that was falling on the surface from the sun, and alpha was 0.7. So that means the surface has absorbed 140 watts of heat energy. But what happens to the other 60 watts? So depending on the ability of that surface to transmit energy or reflect energy, some could be passing through it, that is transmitting through it, and some could be reflected. And we need other parameters, much like absorptivity and emissivity, to determine what happens to that remaining 60 watts of incident energy. So it could happen that 20 watts of energy was just passing through the surface, and that's the transmitted energy, and the remaining 40 watts was just being reflected. And in later videos, we'll talk more about the ability of a surface on how to transmit energy through it or reflect from it. So the important thing is absorption of radiation will increase the thermal energy of the matter, and emission of radiation will decrease the thermal energy of the matter. So it's like putting money or taking away money from a savings account. If you put more money into a savings account, it's going to increase your balance. If you are going to take out money from it, it's going to decrease your balance. So it's like the same thing, absorption and emission can increase or decrease the thermal energy of the matter. So an important concept is if energy is transmitted or reflected by the surface, it's not going to affect the thermal energy of the matter, because transmitted energy means energy passed through the material. It might affect it, but it's not going to change the total energy amount. So it's like, imagine some amount of money is entering the savings account and it just left the savings account. So that means it's not going to change your balance. And reflected energy means it did incident upon the surface, but then it was just reflected away from it. So it did not have anything to do with increasing or decreasing the thermal energy that was already there in the matter. Much like emissivity, absorptivity also depend on surface material and finish, and most importantly, it also depends on the nature of radiation. So this means absorptivity of surface to solar radiation and absorptivity of the surface to radiation from oven walls will not be the same. So we must keep in mind that depending on the nature of the radiation, it might have some impact on the absorptivity value of a surface. When we calculate G, we did mention that irrespective of the source, whatever energy is falling on the unit area of the surface, we're going to call them incident radiation. But that does not mean that the absorptivity of surface to any kind of radiation will be the same. So now let's look at how these concepts help us in terms of real world applications. So for example, if we have some food which we can represent by a surface, and we place that food in a kitchen table surrounded by the walls of the kitchen, or maybe inside an oven rack which is surrounded by the oven walls, and what's going to happen, so how much heat is going to be transferred due to radiation. So in order to understand that, we need to know about radiation exchange between a small surface and a large surrounding. So again, we take a surface and we have some gas around it, and we have the temperature of the gas to be T infinity and its heat convection coefficient to be H, and then the surface can exchange some heat transfer via QCONV via convection, and the convection heat flux would be given by QConv double prime. We are also going to assume something. We are going to assume that the emissivity of this surface and the absorptivity of this surface are equal. So we are assuming it, but it's actually true, and there is a proof of it which we'll see later. We are also going to assume that the area of the surface is given by A, and the surface temperature in absolute scale is Ts, much like before. And now we are going to represent the radiation heat flux that is leaving from the surface. So whatever the amount of energy that is emitted by the surface, we are going to call it Q rad double prime, and this time we are actually referring to the fact that this surface might receive some energy or absorb some energy, and it's also emitting some energy, and this Q rad double prime is representing the net amount, the total amount that is actually leaving from the surface. So now imagine there's a large surrounding, so maybe a gas, so let's call it air. So the surface is placed in a room with air, and that air is then called the surrounding, and it has its own temperature, TSURR, or temperature of the surrounding in Kelvin scale. And it does not necessarily have to be air, it could be the walls of the kitchen or walls of the oven. So long it's a large object that is completely enclosing the surface, we are good. So now we can calculate how much radiation is exchanged between these two objects, and by these two objects I mean the surface we are considering and the surrounding of the large object. We can also consider this gas, which is shown in the figure, to be very small, but to keep our analysis simple, we are going to ignore it for the moment. So the first thing is we have to assume the surface temperature and the temperature of the surrounding, they are not equal, because if they are equal, then according to the zeroth law of thermodynamics, they can't really do any heat transfer, right? So in order for this analysis to be valid, they cannot be at the same temperature, because if they are at the same temperature, then there is going to be no heat transfer. So now we can say, since the surface is enclosed by a large surrounding, we can write the emission from the surrounding, assuming it to be a black body, right? So what does this mean? So we're going to try to understand this equation. So this surrounding is also emitting radiation, right? And if we assume that the surrounding is a black body, then it must obey Stefan-Boltzmann's law. And Stefan-Boltzmann's law's equation gives us sigma times the temperature of that object to the power 4th. So that's the amount of energy that is leaving from the surrounding. But we have assumed it to be an ideal black body, right? So that's why we're not saying whatever the emissivities or absorptivity of the surrounding. So we're just writing this portion. So this is the amount of energy. The right hand side of this equation represents the amount of energy that is leaving the surrounding. But the question is, whatever the amount this surface absorbs, how can we calculate it, right? So if the surface absorbs the energy, that's actually an incident radiation, because we're not considering the effect of this gas or any other stuff. So that means the incident radiation is given by G, And since this surface is completely enclosed by the surrounding, that means whatever the surrounding was releasing from it, it must be received by the surface in its entirety. So we know the surrounding is releasing energy of the amount sigma times T surrounding to the power 4. So that means the surface must have received the same amount of energy that was given up by the surrounding. So that's why we can say these are equal. So if these two things are equal, now we can also assume that the surface to be an enclosed gray surface. So that means it's a real surface, right? And for this type of gray surface, we can actually assume this to be true, that the absorptivity of that surface and the emissivity of that surface are equal, and there is a proof of it which we will see later. And now we are ready to go ahead and calculate what was the net radiation that was transferred from the surface. So we said the net radiation that was transferred from the surface was given by Q rad double prime, and this means whatever the energy that was leaving the surface and whatever the energy that was entering through the surface. And we can write the left hand side to be simply radiation heat flux from the surface. So if the amount of energy given up by the surrounding was 500 watts, that must be going to the surface, and say if the surface was releasing 200 watts, so you can just simply put those values, 200 minus 500, and we get a negative value of 300. That means the surface was not actually releasing any energy, rather than it was actually gaining 300 watts of energy. So if this thing comes out to be negative, that means the surface is actually receiving energy. If this thing is positive, that means it's actually releasing energy. So all we have to do is write the radiation heat flux from the surface is the emission from the surface. So whatever energy that was emitted from it, and whatever the irradiation that was on the surface. But in this particular case, we know that whatever the irradiation that was, it was coming from the surrounding, because we are neglecting this gas. So let's quantify this. So we can write the left hand side to be Q red double prime, and the right hand side we can replace that red word, those red words, with this red equation, because we can assume this surface to be a gray surface, which means this is the amount of energy that was leaving, or emitted energy, because it is not a black body. At the surface temperature, E subscript B gives us the emissive power of a black body, and we just multiply it with the emissivity to get whatever the amount of energy that was leaving the surface. And for the blue quantity, which we mean the irradiation on the surface from the surrounding, we are writing alpha times G, because we know whatever the incident radiation on this surface, that is given by G, and we can multiply it with the absorptivity of the surface to get the actual amount of absorbed energy that is falling in the surface. So the blue quantity means whatever the energy that was falling on the surface, the red quantity means whatever the energy that was leaving the surface. So this can be simply write as this. This quantity refers to emission, and because it's a non-black body, that's why there is an epsilon here, because if it was a black body, you can just simply put epsilon equals 1, and it would not going to be there. And for the absorption, similarly, because it's a non-black body, we have to multiply with its absorptivity. But we know that the emissive power of a black body is given by sigma times Ts to the power 4, right? So there's a mistake in the slide, and the sigma is missing. So we are going to write this here, that from Stefan-Boltzmann's law, that epsilon times sigma times Ts to the power 4 is going to give us that emission from a non-black body. And similarly, we are just going to subtract the alpha times G, or the absorption, to get the radiative heat flux from the surface. But for enclosed surface, we know that epsilon and alpha are equal, so we are just going to substitute that in our equation, and then we can write this G to be sigma times T surrounding to the power 4, because we have already established that for enclosed surface, whatever energy that was released by the surrounding, it must be absorbed by the surface, or by the enclosed surface. So we can just combine these two and write this equation as Q rad double prime to be epsilon sigma times Ts to the power 4 minus T surrounding to the power 4, and this gives us the radiation exchange equation. So let's put in this equation in a green box, and this equation actually gives us the difference between the released thermal energy due to emission of radiation and the thermal energy gained due to absorption of radiation. So whatever the energy that was leaving, whatever the energy that was gained by the surface, this equation provides you the difference of that, or the net difference of that, in form of a heat flux. So that's why we are calling it the radiation heat transfer equation. And this equation can be even further simplified. So we know this algebraic formula that a squared minus b squared can be factored into a plus b times a minus b. So we have the fourth power. So basically we are going to get factor in the form of squares. So if we apply this equation once, we get an equation like this, and if we apply it again on this part of this equation, we get something like this, that q rad double prime equals epsilon sigma times ts squared plus t star squared times ts plus t star times ts minus t star. So the most important part of this equation is this difference term, because now it's a linear term because the power of these terms are 1, whereas they were before in the form of fourth power. So now what we can do is we can calculate the actual amount of heat that was transferred, so not their rate. So from the heat flux definition, we know that the q rad double prime is the amount of heat transferred in the form of watts divided by the area, because heat flux refers to heat transfer per unit area. So we can actually write it in this form, that q rad double prime equals q rad, and we know that this heat flux, the radiation heat flux, is given by this equation, the radiation heat transfer equation. So after going through a few steps, we can simply write q rad, that is this term, which is measured in watts, is given by this equation. So basically we are just multiplying the heat flux with the area of the surface. And if we do that and rearrange the terms, we can write it like this, that the amount of radiative heat that was transferred is given by this equation, and we are going to combine all these terms in red and call it H subscript R. That is, we are going to call them radiation heat transfer coefficient, and there is a reason behind that, because if we write the equation in this form and put it in this green box, that q rad equal hr, a times ts minus t sir, whereas hr is given by these red terms. If we do that, then actually we have written this equation in the similar form as the equation of convection heat transfer, because for a convection heat transfer, we know the equation was given by the amount of heat that was transferred by convection was given by H times AS, where H was the heat convection coefficient, and the temperature difference between the surface and the moving fluid. But this time we are writing the radiative heat that was transferred is given by the radiation heat transfer coefficient times the surface area times the surface temperature minus the surrounding temperature. So the difference between the temperature of the surface and the surrounding. So this equation is called the linearized rate equation, because the equation contains the difference of temperature which has powers of 1. So in this equation, all the terms have the power of 1, and that's what it makes it a linear equation. But we know that HR is given by this large equation in the blue box, and it is pretty much similar as to heat convection coefficient. But there is a big difference, and the difference is the radiation heat transfer coefficient depends very strongly on temperature. So heat convection coefficient varies with temperature. Radiation heat transfer coefficient also varies with temperature. But for radiation heat transfer coefficient, we can see from this equation there is a temperature term Ts squared, which is multiplied with Ts, so that gives us Ts to the power 3. So that means it actually varies with temperature, but not linearly, but in the power of 3. So we can actually write HR is proportional to Ts cubed. So that means the effect of temperature on radiation heat transfer coefficient is pretty strong. HR also depends on emissivity, and because emissivity and absorptivity is in this case are equal, we can actually call it that HR depends on both emissivity and absorptivity in this instance. And the reason is because we can see emissivity is present in the right hand side of this equation. And again, just to keep in mind, it is different from convection heat transfer coefficient because it varies very strongly with temperature, whereas convection heat transfer coefficient depends weakly on temperature. So these are the two different forms of radiation heat transfer equation or radiation heat exchange equation. So the equation in the red box is much simpler to remember. We can just use that equation to derive the equation in the green box, which is the linearized rate equation. For the second equation, we just have to apply the algebraic formula of a squared minus b squared twice. And we can also remember what's the radiation heat transfer coefficient from this equation. So in practice, it's much more easier to use the equation in the red box, and if there is a need that arises where we have to calculate the radiation heat transfer coefficient, we can simply derive it by applying that formula twice, and instead of keeping these complex formulas in mind. So in practice, we have to remember that convection and radiation heat transfer both actually are always present, and we have to make a case to neglect either one of them. So if the temperature of the object is not very high, we can say the fourth power of that temperature is also not very large, and we can ignore radiation heat transfer. But in general, radiation heat transfer is always accompanied by convection, and it's a safe practice or good practice to consider both of them. And low temperature, we can ignore radiation heat transfer because it's generally small. And in ideal world, we should always consider conduction, convection, and radiation heat transfer modes at the same time. But keep in mind that's going to make your analysis complex or time consuming. If we are going to consider convection and radiation heat transfer together, we have to write the total amount of heat that is transferred from that surface. So we knew because of that gas there was some convection heat flux that was going on, and because of the surrounding and the surface exchanging the radiation, we said there was a radiative heat flux that was also going on. So what we have to do, instead of using the fluxes, we have to calculate the actual amount of heat that was being transferred. So we just have to multiply them with the areas, and we can write Q total equals Q conv plus Q rad. So all of these are in watts, and we know Q conv is given by H times AS times Ts minus T infinity. So the temperature of that gas, and the radiative heat transfer is given by the radiation heat exchange equation, epsilon times sigma times A times Ts to the power 4 minus T surrounding to the power 4. So now let's look at an example. So imagine there is an object that has a surface area of half meter squared, emissivity of 0.8, and temperature of 150 degrees Celsius, and it is placed in a large evacuated chamber whose walls are kept at 25 degrees Celsius. So the question asks what is the net rate at which radiation is emitted by the surface. So basically the emissive power, and it also asks what is the net rate of radiation heat exchange between the surface and the temperature walls. Now let's look at the sketch of the problem. So here is the object. It's surrounded by the walls of the evacuated chamber. The walls are kept at 25 degrees Celsius at 298 Kelvin. The object has 150 degrees Celsius temperature, which comes out to be 423 kelvins. It has a surface area of half meter squared and epsilon of 0.8. That is given in the statement of the problem. So this red arrows refers to emission of energy from the object, and the blue arrows means irradiation to the object from the chamber walls, because the chamber walls are also emitting energy because of its own emissive power, and whatever it is emitting, because it's enclosing this object completely, they must fall into the surface of this object. So we can make this assumption because the chamber is evacuated, so there is no fluid or anything, so there is no convection going on, and there is no contact between the object, that is the surface, and the walls. So that means there is no conduction heat transfer. And because this surface is completely enclosed and its area is much less compared to the chamber wall, so it's much smaller compared to this whole evacuated chamber, we can safely say that we can use the radiation heat exchange equation, because if this condition is true, that means the alpha and epsilon of this object can be safely assumed to be equal. But if the area was much larger, the analysis would have been much more complex, and we cannot use that simplified analysis of radiation heat exchange equation. So we can make all the other assumptions such as a steady state problem and whether the thermal properties are constant and so on, much like I did in any other heat transfer problems, but I'm not going to write them here. So I'm just going to directly write the emission rate is given by the emissive power times A, because it's asking what's the net rate at which radiation is emitted by the surface, so it's asking for a watt value. So we know the surface area, we know the emissive power, because we can simply write it to be epsilon times sigma times T to the power 4, because it's not a black body, the object is not a black body, so we need its emissivity, and we can just put in all the values, make sure we calculate the temperature in kelvins, and we'll get 726.1 watts. So that's the amount of energy that is emitted by the object, and it's represented by these red arrows. Similarly, we can just use the radiation heat exchange equation to come up with the net rate of radiation heat exchange between the surface and the chamber walls. So the radiation is then given by, if we just put all the values in here, would be 547 watts. So this is not the value of the blue arrows, but it just means the net rate. So if we just subtract the value of the blue arrows from the red arrows, the energy represented by those arrows, then we would get the net rate to be 547 watts. So that's the amount of heat energy that is actually being exchanged by the surface and chamber walls due to radiation. So there is a important thing we must keep in mind, that these rates will only be present initially. So as soon as we put the object inside the chamber walls, we are going to see these rates. But with time, they are going to change. With time, this hot object is going to get cooled because energy is leaving from it, and the surrounding is receiving energy from this object due to radiation. Its temperature is going to increase, and if these temperature values are not kept same, they vary, they are also going to change these values. So Q emit changes the temperature, and also Q rate changes the temperature of both of these two things. So we are going to get different rates at different times. But when these walls would ultimately increase, their temperature will increase and respectively decrease, there will be finally a steady state that would be achieved. So let's summarize what we learned today. Radiation heat transfer takes place when surfaces exchange radiation due to emission and absorption, which is also called irradiation. And emission of radiation can be quantified by Stefan-Boltzmann's law. And the black body obeys Stefan-Boltzmann's law, but real surfaces does not obey it, so we have to use emissivity and absorptivity to quantify their emission and absorption of radiation. Radiation heat transfer coefficient depends strongly on temperature, which is a big difference from convection heat transfer coefficient. Radiation heat exchange equation for an enclosed surface by large surrounding is given by this equation in the red box. So Q rad times epsilon sigma A times Ts to the power 4 minus T surrounding to the power 4. So thank you for watching this video. In my next videos, I'm going to solve problems on radiation heat transfer.